the class aren't
overlaps with optimization, which is trying to minimize loss, and we will talk about this today primarily. And of course, these two disciplines kind of fall under the artificial intelligence umbrella. Now, I'm not really fond of the term AI and artificial intelligence just because it's a very broad catch-all marketing term. I've seen the definition of artificial intelligence just in the past 10 years become more and more liberal, and we'll talk about annealing, and I will do my best to talk about annealing, JK. I mean, I can talk about simulated annealing and other techniques. So, like I said, we're going to be building from exciting from scratch models in Python. Python's great, easy to learn language, but like I said, it's really slow. It doesn't compile, or it doesn't compile into bytecode or low-level machine code, and because of this, it will struggle to scale even with modestly sized data sets. And this again will be the cost of learning using Python, but it's going to. But I think that you're still going to get a lot of satisfaction from today. So you can also learn, if you really get interested in building machine learning from scratch, you might want to consider learning another programming language that is statically typed and compiles, like C or C++, Java, Scala, Swift. So you'll have more success scaling up these machine learning algorithms, and so just keep that in mind. Otherwise, we're going to learn Python today. Yeah, and AJ does make a good point. Also, Python being a slow language is only in the context of high performance computing. If you're writing a web server or something, the most expensive thing for you would be the network and database calls. Python's own speed becomes irrelevant. Then absolutely, no, 100% agree. So yes, that is true, and that is a nuance. Thank you for pointing out. Is that yes, when it comes to high performance computing, yes, Python is slow. But if you're doing things like web applications, Python is not the thing that slows down your application. It's usually things like networks and connecting to other servers and so on. So CI says, I am here to get comfortable with Python, and AI tool libraries have many Python raw code for different neural network algorithms, RBM, as well as basic neural deep nets. Awesome. Well, I think you're going to feel pretty at home here. We're not going to focus primarily, our primary focus is not going to be neural networks today, although we will talk about in the last section. It's going to be the other machine learning algorithms that exist. But you'll find that, for example, linear regression, logistic regression do play a large role in neural networks. Yeah, so this will be a fun crowd today to teach. And yeah, you can use Rust for machine learning. I've heard a lot of people love Rust up and down. And from my understanding of Rust should be a perfectly performant computing platform. Okay, I've heard a lot of people use Go as well and have success with it. Okay, so let's talk first about linear regression. By the way, folks, we just had a freeze here in North Texas last night, hence why I am all bundled up, because we're waiting. I forgot to turn on our heater last night, and so we're waiting for it to catch up. But there was also a short power outage, so in the event you lose me for a moment, I do have some backups. I can tether to my mobile, my iPhone, and continue this class. I have done that before in past winter storms, so just hang on for a moment, and Andrew will keep you. Will tell you to stay put, and I'll get it back online as soon as I can, in the event that happens. So in practicality, machine learning is often about two tasks: regression and classification. So let's start with regression, particularly the simplest one called linear regression, which finds the best fit straight line through some points. So here is a simple two-dimensional plot of two variables. So you have the x and y axis. The x-axis is the input variables, also called the independent variables. The y-axis is the output variables, also called the dependent variables. So we want to find the relationship between these two variables so we can make predictions on new data. And this is where I find it gets interesting. There's two divergent schools here. There's the The machine learning, computer science folks, who the only thing they really care about is making good predictions, and they don't really care as much about explainability. And there usually is much more of a computer science slant in the machine learning school. And then there's the statistical mindset, where the goal is not necessarily to make good predictions. It's more to understand the relationship between the variables. So this is why linear regression is used by both statisticians and machine learning engineers, but they often use them in different ways, with different goals in mind. So I think it's always good to walk the middle of the road and know and understand both schools of thought, because it's very situational which one's going to be more performant. So, and this is why statisticians even call their models, they started to rebrand a lot of models as statistical learning, because they don't want to use the term machine learning, but they will call it statistical learning. So we want to so for both schools of thought, though, we're trying to find a line that best fits these points. And you probably know, you all are probably familiar with the function y equals mx plus b. So we already know the data points, the x and y values. So the x and y variables are not what we're interested in. It's the m and b coefficients. That's the slope and the intercept. We need to solve for that. So we have to first ask what defines a best fit anyway. Yeah, and we're definitely going to talk about logistic regression in the next section. And yes, there is a huge tie-in to neural networks, because logistic regression kind of is a simple neural network in a way. So, pretend you drew any straight line through the points. You're not going to be able to fit a perfect line because the points do not exist on a straight line. And machine learning models are never perfect because real-world data is never perfect. So, but you can use this line to make estimations and to make predictions on new data that you have not seen before. Even if you have this error called loss, and loss is the accumulation of differences between that line and those points. So it's helpful to, even if we do have loss, even if we do have errors, it is still helpful in making predictions. And we can use this to model things such as how much y growth there will be at x time in the future. So when you plot a given line, notice that there is a difference between the predicted y values and the actual y values for our observed data. We call these residuals. So those differences between the points in the line, you see, those are residuals. And let me ask you folks this. How do you think we would measure those residuals in aggregate? So how do we total up those residuals? And I say total in quotes. What do you think? So if we're trying to measure the overall quality of a line and how well it fits these points, and we accept as our rule of thumb, these residuals have something to do with it. How do we measure that in total? What do you think? This is a pretty large class today, so I'm sure somebody knows the answer. I'm sure people definitely have theories on what they would intuitively try. What do you think? If we have all these residuals, how do we aggregate those residuals? So I got one person proposing absolute values, and that is legitimate. So you can take because some of those residuals are going to be negative, you can take the absolute values and just sum them all together. I will say this, though, absolute values are mathematically inconvenient to work with. And I got a couple of other answers here. So some people are saying Euclidean distance. Some people are talking about variance. But the sum of the squares is really what I'm looking for. So the sum of squares is the answer. So to solve for the m and b values, we need an objective to minimize total residuals using a loss function. So we don't necessarily want to sum up the residuals because the negatives are going to cancel out the positives. The absolute values, yes, that can technically work, but they're mathematically inconvenient to work with for reasons regarding calculus and derivatives. So as several folks proposed, the sum of the squares is the best approach. Take each of those residuals and square them and then sum them together. This has the benefit of penalizing large residuals by making them even larger. It also will take negatives and turn them positive because when you square a negative number, it's positive. Negative times a negative is always a positive. And also, it's just mathematically easier to work with, especially if you're going to be using derivatives. And I'm not going to really get too much into the calculus in this class today, but I do talk about that a lot more in my book. So using gradient descent in linear regression in chapter 5. So we can then find the m and b values that will find the sum of least squares. I'm just posting a few links here. Okay. To calculate the sum of squares, and then CI says microeconomics starts here, and then the random walk. Yeah, I was actually reading the other day that random walks. I mean, because I kind of understood the purpose of the random walk exercise. It's interesting, but it apparently falls apart in higher dimensions. So when you have more than 2 dimensions, the random walk starts to fall apart. And I've been meaning to deep dive into that topic and just trying to probabilistically understand why. I think I know the answer to it, but that's something that I've been meaning to look at in the future. So anyway, I digress. So to calculate the sum of squares, here is just a simple spreadsheet that walks through. So for given m and b value, which you see modeled right here, those m and b values are chosen. We'll talk about how to choose them later. But for that given m and b value, that given line, you see we have those 10 data points. The predicted y value is going to be m times x, the given x value, plus b. That'll give you your predicted y value, the value that would be on the line. And that difference would be the residual. You square each of those residuals, and then you sum them together, and that will give you a sum of squares of 28.096. Any questions so far? Now, somebody asked, is there any explanation why we use sum of squares or root of sum of squares? I see that it has something to do with the calculus, but I can't seem to recall. So there are other methods to fit a line to some data points. And every mathematical model that we use is based on some heuristics. And by heuristics, I mean rule of thumbs, things that prioritize certain objectives or theories that we believe will lead us to the solution. So the sum of so like I said, we could there are other models, there are other techniques besides the sum of squares or root of squares to fit a line. But that is the most common approach just because it seems to produce a line that most people can agree on. Yes, that's a good line to fit through those points. And we'll talk about how to fit the m and b values, but to measure loss, we choose the line. And we'll talk about overfitting and variance as well, which is another thing you have to consider, in how you fit a model. So, solving for a fit. Now we have a loss function, the sum of squared residuals. So how do we find the m and b values to minimize it? So this is how I'm going to circumvent using any calculus here. So watch closely. So if I need to find the m and b values, what I can do is I can randomly increase or decrease m and b with random values from a standard normal distribution. You can also use a t distribution, which has fatter tails, but the normal distribution should work just fine. But if you want to have fatter tails, that will give you more diverse moves. But like I said, for the purposes of our exercises, the normal distribution will work just fine. Now, the normal distribution, the standard normal distribution, has a mean of 0 and a standard deviation of 1. So notice that bell curve. It has a mean of 0, and most of the values that we're going to randomly sample are going to be close to 0, meaning that they're really small. You'll have really small positive numbers and really small negative numbers. So this will allow us to make fine adjustments to m and b as we add those values to it. But occasionally those tails have larger moves, so if we have to make a big jump, we'll have opportunities to do so and make larger jumps in the value change for m and b. So this is how we completely circumvent doing any calculus, which again I do in my book, but I like using hill climbing as a way to introduce machine learning because it just removes a lot of hurdles to do so, and you kind of understand there's less moving parts to understand here. So here's how you implement hill climbing. Start with a random or initial solution, even if it's poor quality, even if it sucks. But you're going to repeat the following steps for a number of iterations until the solution just doesn't really improve anymore. Select a random part of the solution and change it. If that results in improvement, we keep it. It's easy, right? It's like a much more controlled brute force. So let's walk through how to do this. Let me spin up a notebook real quick. Also, let me share the GitHub for this class. And just for one administrative task, I'm not going to really rely on them for much else other than importing the data. I have this point class that's just going to hold an x and y property. And in each point object, I'm going to read the CSV, which you can see right here is just 2 columns of data, very simple, very basic. And that's the exact same data we saw on the slides earlier. And then we are going to iterate each of those rows, build a point object off the x and y values. We are going to start m and b, the slope and the intercept, at 0. I'm going to use 150,000 iterations. So epochs is a fancy name for the number of iterations. And then n is going to be the number of points. And I'm just going to make it a floating point value so I can easily divide it. And then I'm going to start my loss at an extremely large number. So I can make this positive infinity, or I could just make it like a ridiculously large number. So that I know when the iteration starts, this will be overwritten. So for each iteration, I'm going to randomly adjust m and b by pulling from the standard normal distribution. This will give me 2 values to adjust m and b with, so I add those adjustments. Remember, these random values are based on that bell curve, where we're going to get mostly small changes near 0, but occasionally we will adjust. But we will get larger moves if m and b need to make a larger adjustment. And then I'm going to calculate the new loss, iterate each of those points, take the actual y value, subtract the predicted y value, which will be m times x plus b for each of those points, square that, add that to my loss. Finally, if my loss is improved, I keep the new values. Otherwise, I revert and undo that random adjustment. So only if my loss improves, meaning it's less than the best loss I've found so far, I will undo that random adjustment. And there we go. So you can see that after it finished, it gave me approximately 1.938x plus 4.737. And that is the function that best fits to these points. at least according to our hill climbing. Them used for deep learning. Now this is where it gets interesting. So linear regression. So hill climbing is gradient descent and stochastic gradient descent are just one of several optimization algorithms. They're actually a cousin to hill climbing. There is also simulated annealing. There is also genetic and ant colony optimization. So there are other optimization algorithms. And I just showed you one that did not require any calculus. Yeah, it's a little bit more brute forcey, but the thing is, even stochastic gradient descent is random based. And if we have time, I'll talk about this a little bit later. I definitely talk about it in depth in my book. And sometimes we find for certain models, we find shortcuts to avoid having to use these optimization algorithms altogether. So for example, linear regression, state-of-the-art techniques don't use gradient descent or hill climbing. Instead, what they will use is matrix decomposition techniques, which I do talk about in my book. But like I said, this is one way to do machine learning from scratch to kind of understand how learning works. And there's also different heuristics, different optimization algorithms to perform